Hi, my name is Rebecca Lisowski. I'm in Mr. Kaplo's Honors Physics class, and this is my solution to problem number 30 from chapter 12 on page 348. So this question is broken up into three parts. Part A reads, determine the length of an open organ pipe that emits middle C, which they give to us as 262 Hz, when the temperature is 21 degrees Celsius. So the first thing you should do when you start any problem is to write down what you know, and we're going to do this off to the right. We know that the frequency is 262 Hz. Now you'll notice that it says f sub 1, which you should know stands for fundamental frequency, and I'll explain why we're assuming that in a minute. So the next thing you should recognize is that the problem gives you temperature, which is 21 degrees Celsius. And when you see temperature given in a problem, you should remember the equation velocity equals 331 plus 0.6 times t, where t stands for temperature. This equation allows you to solve for the speed of sound traveling through air at different temperatures. Now we're going to plug in 21 for t and solve, and we're going to end up getting the speed of sound is equal to 343.6 meters per second. And we're going to write this off to the right. So now we have 3 out of the 4 components of the equation v equals f times lambda, where v stands for velocity, f stands for frequency, and lambda stands for wavelength. And so now here's why we're assuming 262 Hz to be the fundamental frequency. Unless the problem states otherwise, you should always assume that an object is vibrating at its natural frequency, which is also known as the fundamental frequency. So to help us visualize this, I drew a little sketch of an open tube resonator at the fundamental frequency. And you'll notice there are 2 nodes at either open end of the tube and 1 antinode in the middle. You should know that at the fundamental frequency, wavelength is equal to twice the length of the tube, or that half of the wavelength is equal to the length of the tube. So knowing these 2 equations, we're going to substitute 2L in for lambda. You can also choose to solve for wavelength first and then plug that in to solve for length, but I think it's easier to plug in 2L directly. When we do this, our new equation looks like v equals f times 2L, and when we move things around to isolate the variable we're looking for, in this case L, we get v divided by f equals 2L. Now we can simply plug in the numbers we have and solve. 343.6 divided by 262 is equal to 2L. When we simplify, we get 1.31 is equal to 2L, and we divide that by 2, and our final answer is 0.656 meters. Keep in mind that our input numbers had 3 sig figs, so our answer should also have 3 sig figs. Part B of the problem asks, what are the wavelength and frequency of the fundamental standing wave in the tube? Luckily for us, we already know what the fundamental frequency is because we assumed it in the last problem. We said it was 262 Hz. So that answers half of the question. Now we just need to find wavelength, which is just as easy. If we revisit the equation v equals f times wavelength, we can plug in our numbers and solve for lambda. We rewrite our equation to get lambda by itself, and we plug in our numbers and solve. We should get 1.31 meters as our answer. Now you can also find wavelength by multiplying the length of the tube by 2, since we established on the previous slide that at the fundamental frequency, wavelength is equal to twice the length of the tube. But in the end, our 2 answers are 262 Hz for the fundamental frequency and 1.31 meters for the wavelength. Finally, part C reads, what are the wavelength and frequency in the traveling sound wave produced in the outside air? So if we bring back our sketch from the first part of the problem, this will make it really easy to understand. Because the organ pipe is open on either end, that allows air to freely travel between the inside and outside of the tube. This means that the air inside the pipe and outside the pipe are under similar conditions. When the conditions are similar, whatever frequency causes the pipe to resonate will be the same frequency that travels in the outside air of the system. And if the frequency is the same, that means the wavelength is also the same. So the answer to this part of the problem is simply the frequency of the wave in the outside air is 262 Hz, and the wavelength is 1.31 meters.